Hi, I thought I'd start this lesson with a photograph of this mountain. It's a mountain in the Northern Lake District in England called Skiddaw. And I've shown this because Skiddaw is part of a large metamorphic aureole. There's a very big granite pluton buried deep beneath this mountain that's metamorphosed all the rocks around it. What makes it quite unusual is that, as well as the metamorphic rocks around the side that we'd expect to see in a metamorphic aureole, what we see at the top of Skiddaw is actually the rocks above the Pluton that have also been metamorphosed. Anyway, what I want to do in today's lesson is have us think about some of the features of a metamorphic aureole, like the ones we see at Skiddaw. But to start with, I want to look at the answers to question 4 on page 7 of your Theme 6 booklet. So you need your booklet. Let's go. Okay. For question 4, I've given you the names of 4 of the rocks that we need to know. We've got marble, we've got schist, we've got slate, and we've got metaquartzite. And I ask you to fill in, using the graph that you worked on last lesson, the rocks that form at these different conditions. So, first of all, we have marble. Marble forms under low pressure and high temperatures. It's a contact metamorphic rock. It's the type of thing we would find in a metamorphic aureole. Slate forms under high pressure and relatively low temperatures. It's where mudstone gets squeezed as it starts to get buried within the earth. So the pressure is going to be increasing. The temperature isn't particularly great though. It's why there's no new minerals that are growing within a slate. Schist, though, is formed under higher pressure and higher temperatures. It's a higher grade metamorphic rock, which is why schist has been recrystallized more. It's why we get the growth of the mica. And finally, then metaquartzite. That's another contact metamorphic rock, formed under low pressure and high temperatures. So if we now fill these in terms of the type of metamorphism we see, contact and thermal metamorphism, or contact or thermal metamorphism, I apologise, is marble. Slate is regional. Schist is also regional metamorphism. And metaquartzite is contact metamorphism. Okay then, let's have a look at some of the minerals then we find in each of these rocks. So for marble, the main mineral is calcite. Very distinctive, drop some acid on it, marble will fizz. For schist, the main mineral is mica. You might find, you could put garnet down as well. There are lots of schists that do contain garnet, but not all of them do. But to be a schist, it needs to have mica in it. For slate, it can have some mica, it can have some quartz. Clay is actually a really important mineral in slate, but it's really hard to see because slate is so fine grained. And finally, metaquartzite, fairly obviously, is going to be quartz. Can look very similar to marble, but this one will not fizz with acid. Also, it's harder. Knowing these minerals, then, we can also then determine the parent rock. Why are these minerals different? marble, the parent rock is limestone. That's why it contains calcite. So if we heat up limestone, we get marble. For schist, it's a shale or a mudstone. Doesn't look much like a shale or a mudstone, but that's what it started out as before it completely recrystallizes. For slate, it's also a shale or a mudstone. Although slate does at least resemble a shale, but that can make it hard to identify. And finally, metaquartzite was originally a sandstone. Now, those of you that had to go at the digging deeper, the minerals that change most are the minerals that we get in a mudstone. Clay in particular. Clay is a weathering product. It forms at the Earth's surface. So if we heat it up to temperatures and pressures that aren't found at the Earth's surface, it's most likely to change. It's why, for example, we can use clay to make pottery. Because if we get it enough to high enough temperature, it will change. Okay. Let's turn to page 8. On page 8, we've got a set of questions there about a metamorphic aureole and some of the information about the temperature and distance from the edge of the intrusion. You've got 3 bits of data here. On the top left there, we've got a map. So this is a view of an area looking straight down. Okay, it's like a bird's eye view. Think carefully, especially about the scale of this map. Okay, how big is a kilometre? Once you've measured that, how big then would 100 metres be? So we can then start to measure some things. Read the questions carefully and have a go at those. Okay. Some of those questions you'll need to actually mark things on these on the map and the graph and so on. Okay. Have a go at those now. So press pause and complete question 5. Okay then, let's see what you've come up with. So question 5a tells us that specimen M formed at 450 degrees centigrade. How far from the Pluton was it formed? Once you've done that, you need to mark on the map where that location was. Well, let's see how we can work it out. Excuse me. So if we know it formed at 450 degrees, we can take a line on the graph from 450 degrees across to our temperature line there, drop it down to the bottom, and we get a distance of about 225 to 250 meters. We can then mark on M about that distance away from the edge of the granite, or the Pluton, sorry. Okay, but that M may not be in exactly that place that you marked on your map, but it does need to be in the limestone because M is a marble. Okay, we know it's marble because we can see we've got it's made of a white mineral with hardness of 3 that fizzes with acid. So it can't be, M cannot be anywhere in the shale. Okay. We're then told that metamorphism occurs when rocks are heated to more than 400 degrees centigrade, and then asks you to draw the aureole onto the map. So let's see, if we 400 degrees takes us to here, so it means the width of our aureole is just less than 300 meters, or about 300 meters. So the aureole then would look like the red shaded area on the map. So we measure out 300 meters away from the edge of that Pluton, and we draw around that. It probably isn't going to be a perfect circle like I've drawn, and it doesn't matter if yours isn't either. I then asked you to draw or to mark on your map where, with a Q, somewhere where metaquartzite might form. Now, for metaquartzite, we need some heat from an igneous rock, and we need sandstone. So it's got to be over there on the eastern side of the map, and it's going to be somewhere below that lava flow. Because it's a lava flow, you'll only have metamorphism at the bottom of that lava flow, not on top. Remember, we looked at the baked margins in theme 5. And finally then, those of you that had to go at digging deeper, if it's a larger Pluton, what we'll see is the same temperature at the start, but that heat will go out further away from the edge of the intrusion. There's more heat coming out of the Pluton. So we'll see a line somewhere above the black line that's marked on the graph. Okay, we haven't got enough information to plot exactly where it would be, but just anywhere above that black line. Okay, as we see the sunset over Skiddaw, we're going to call it quits for this lesson at that. Next time, we're going to have a go at putting all this together. I'll see you then.